First, let me introduce this project. So what is Alzheimer's disease? It is a progressive neurodegenerative disease in which the afflicted experiences a decline in memory and cognition. It is the leading cause of dementia and is a common cause of death amongst the elderly. AD affects many people worldwide, and its numbers are still on the rise. Furthermore, the average cost of caring for an AD patient is a whopping $250,000. There are also indirect indirect societal costs, such as the opportunity cost of the caregiver's time. The number of deaths due to AD has been on an upward trend and is expected to rise further. However, the complexity of AD makes diagnosis difficult. Hence, there is a crucial need for a better system to improve diagnostic accuracy, as early intervention has been shown to be able to improve both patients' and caregivers' quality of life, as well as keep AD symptoms under control and prolong patients' lifespans. This project aims to find the most appropriate deep neural network architecture for classifying AD and cognitively normal subjects, train the selected model, and finally decode the trained classifier to further our understanding of AD by studying its salient features. Next, I'll be talking about the methodology used. An important thing to know is the functional brain activity. It refers to how the neural activity in each anatomical region of interest in the brain relates to various cognitive function. It is measured using fMRI. In particular, we use the resting state fMRI in this project. It is a taskless fMRI where the neural activities are not due to any other stimulus. Functional connectivity is the correlation between the neural activity of two different ROIs in the brain. Studies have found that aberrant function connectivity between certain ROIs are associated with increased cognitive impairment. Thus, functional connectivity ought to contain information on the salient features of AD. In this project, we chose to use a feed-forward neural network as our classifier. FFNs are networks that consist of multiple layers of neurons through which activations are propagated. The number of input nodes correspond to the number of input features, whereas the number of output nodes correspond to the number of output classes. While machine learning algorithms can be highly accurate in providing predictions, they are largely known as black boxes. That is, it is difficult to understand the models. Thus, we use model interpretability algorithms such as integrated gradients, deep-leafed, and gradient sharp to derive feature importance scores, which provides insights on the biomarkers of AD. Lastly, I'll talk about the results obtained. Using an FFN model with 3 hidden layers, we obtain an accuracy of 76.3%. We ran the 3 model interpretability algorithms on the trained model and obtained similar feature importance scores. All 3 algorithms attributed the highest importance score to the parahippocampal gyrus. The functional connection between the inferior temporal gyrus and the uncus is also deemed the most important connection. Moving forward, it is possible to utilize these scores to eliminate redundant features and obtain better performance both in terms of accuracy and efficiency.